I coined that same terminology here also. So it will be like a prelude to what is called an interacting field theory. So just a minute. Admit. Yeah. So it will be like a prelude to interactive field theory, but strictly speaking, I don't do field theory too much. So the field theory stuff will come at the very end, but I want to give you a flavor of what is Feynman diagrams and interacting field theories and all such stuffs. But it will be like to show you that you could have invented the Feynman diagrams by yourself, just doing some integrals. I mean, that's the whole point. That it will not be something too much difficult for you to invent some pretty little diagrams associated with some big, sophisticated or ugly integrals. That's the whole approach. So it will be mostly a mathematics oriented approach, nothing very physics oriented things. I will mention few things which comes in physics, but it will be something like a trickery or tricks to solve some problems or do some integrals, how to do it in a quicker way, in a tricky fashion, and you will get to the answer. Because Feynman diagrams are a technique at the end. It's not something physics involved stuff. It is a technique to solve field theoretic problems, which comes in interacting field theory or scattering theory in quantum field theory. So it is a something like a programming language. It is like you understand, learn a programming language, and using that programming language, you solve some problems which you cannot solve by your usual knowledge. So Feynman diagrams is like a programming language for field theorists. So you should understand that in that way. So let's start. Let's start with something very familiar. I mean, I think probably at the kindergartens you have done such integrals, like the integrals written here. These integrals is very familiar. Anybody, can you tell what is that integral is? Any of you? You know this integral, right?
Gaussian
Yeah,
integral.
this is a Gaussian integral. This is not a Gaussian curve. The function is a Gaussian. This is under the integral. That integrand is Gaussian, but it is a Gaussian integral. Now, can you know? Do you know how to solve it? I mean, you know the answer. Everybody memorize the answer. The square root of pi by pi by 2 pi or something like that. But can you do you know how to solve this integral? So this was actually originally solved by Euler. Yeah, that approach is like that. You first take a square of this integral. I should have called it g1 rather than g. So you square this integral. So you have a dq, integral over dq, where q is a dummy variable which you integrate out. So you square that integral dq and dp. You take another variable dp and square it. Now you go. Now you assume you have a circle in PQ plane, which is these two variables p's and q's, and PQ plane. You assume you have a circle which is q square plus p square is equal to r square, where r is the radius of the circle. But this r is a variable here because q's and p's are variable. It can vary, so the radius of the circle can vary. So you have an elementary area of that circle which is given by dp dq, which is r dr d theta. So you can rewrite your integral, this g square, in terms of the polar coordinates, that is r dr d theta. So you can integrate over r, which goes from 0 to infinity now, and you over theta, which goes from 0 to 2 pi. As simple as that. And your Gaussian function is now become a function of r only, which is exponential of minus 1/2 r square. Now for this presence, now earlier you have only dq, q square, but now you have r dr r square. So for this presence of this r term in front of that integral, you can readily solve it. You can just redefine your r dr as some d omega, and you can write this integral in terms of d omega, and you can find it is elementary to solve it. It is just 1. this integral is 1 and you just got 2 pi. So this is the way to solve this integral actually. So your g1 will be square root of 2 pi. That's it. I mean, most of the cases you we memorize the result. This is like gamma half or something like that. You memorize that it is root pi or something. But this is the way to actually solve this integral. This is not some foreign stuff to you. You don't have to memorize this integral. You can readily do it by squaring the integral. That's a trick given by Euler. It's not given by me. I'm not smart enough. But this is a trick given by Euler. So, is it okay? Any question about these things? Ah, I think it looks familiar. So, let's go to step 2 of our problem. So, what I have done, I rescaled it for a dimensional reason. So, I put a here in front of this q square where this a is a parameter. So if you rescale it, you can easily found that the integral will be nothing but 2 pi by a whole to the half rather than square root of 2 pi. There will be a 1 over a factor, 1 over square root of a factor in that integral. So now let's make it a bit difficult. Now we have another integral g2. Again, it is a much familiar integral, but a little bit more generalized integral, which is like this. That is 1 half aq square plus bq, whose solution is given by this. So how do you solve it? How you used to solve this integral? Anybody? How you
Completing
solve
square.
this integral? You just complete this square. That is, you just make it a. You just take another. You just add another term and subtract that term to complete the square, and you then redefine some variables and do the integral. But let me show you a more formal way to do this integral. This is the same thing. I will complete the squares, but it is there is a formal way to do that, which we will use later on. So what is the much formal way? Uh, let's see the formal way to do this integral. So what you will do? You will take this exponent of this exponential and you call it some p of x, and you will find the maxima of this exponent. So you take a derivative. Sorry, it will be q, not x. It will be q. Just a typo. So you will find the derivative of this function p of q with respect to q, and you will calculate the maxima of p. So what is that maxima? That maxima will be at q is equal to b by a, which is b square by 2a. Now you rewrite pq minus p max, which is this, and that will complete your square. So pq minus p max plus p max. So pq minus p max will complete your squares. You can readily see that you can write it as minus a over 2 q minus b by a whole square. And your exponent you can now write in terms of this completing the squares, that is a by 2 q minus b by a whole square plus b square by 2a. Fairly easy stuff. Now this b square by 2a is a constant. It is independent of q's. So you can take it out and you can redefine your variable q minus d by a some y or something, and you can then integrate. And now this integral is exactly the earlier integral, which is this one. So you know the answer. You can readily write down the g2. But let me show you this answer in a slightly different way. It's exactly same, but I will write it in a different manner for a future purpose. Let's so the g2, the integral, is given by dq exponential of minus half q a by 2 q plus bq. That's your half aq square, and this is bq, which I will write as 2 pi over a whole to the half exponential of half b 1 by a b. That's the form. That's the form you have in your answer. So, is it okay to everybody? Anything difficult for you? This is familiar. Okay. So now go a little step further. I'm doing some elementary integrals, nothing much. Some kindergarten level integrals. Now, now if we want to integrate over some functions rather than q, if these q's are like some parameters or variable. Now, if you have some functions which is a q as a function of t, then you have to think of these q's in this expression. You have to think of these q's in this expression uh, with something like uh, vectors or multi-dimensional arrays, like, and this is like some matrices or some n cross n matrices, because we want to generalize this in the function space. So now you are at in a parameter space, and later on we want to generalize to do some more realistic stuff like in field theory. So we want to generalize this for some uh, function space. So for that, we first need to generalize this integral to the space of matrices or space of arrays of vectors. So we'll start with an n-dimensional vector. Now this q with a subscript tilde. Just a minute. Now this q with subscript tilde is an array or a vector which has some n components, which I just denoted by some qj's, with this j's takes from 1 to n. So these queues are like vectors. This is a straightforward generalization from this parameter space to some vector space where these queues are now vectors. And we consider the integral, which is the same integral, but now it is a multi-dimensional integral, which is an n-dimensional integral, where I call it a G3. It is a more difficult step, which is dq1 to dqn exponential qi aij, because I have to generalize this a factor. Now aij are not just some numbers, they are matrices, they are n-dimensional matrices. So what kind of matrix are they? Can you guess? Anybody? These aij's, what kind of matrices they has to be? They can't be any random matrices. These are n cross n matrices. Qij's are arrays. So we can write it as q transpose aq, the same thing I have written here. So what kind of matrix aij has to be? Or they can be any random matrices, or there can be any specific kind of matrices. You can clearly see that you can interchange this I and j from Q. So you can write this Qi here and Qj here. So if you change this I and j, the structure of this exponent will be same. So Aij has to be a symmetric matrix at least. As at best, we can say that Aij has to be symmetric, because these Qi and Qj's are not two different Qs; they are same. So if you interchange Qi and Qj, these A's are just n cross n symmetric matrices. So we will have an n cross n symmetric matrix, which is A. Now we have a generalized version of Gaussian integral, a multi-dimensional Gaussian integral, if you want to say that. That is q dnq. I just written this measures by dnq, and this is exponential of minus r q transpose of q. Now, can you do it? Any idea how to do it? How you can do it? Any idea from anybody? Now, earlier we have done that. I mean, from earlier lessons, you have two lessons from these two integrals. We have this integral and that integral, which is exactly familiar. You know how to do it. Now, just we generalize it in terms of arrays, multidimensional arrays. Now, Q's are vectors and A's are matrices or symmetric matrices. So, how to do this integral? Which function? I mean, why you will find the maxima, because you don't need to complete the squares. Yes, if we have some other stuffs like some BQ kind of stuffs or B transpose Q kind of stuffs, then we need to find the maxima. Eigenvalue, I got an answer. Eigenvalue of what? Close enough, but what you do with those eigenvalues? It's pretty close. Any guess? Aha, good guess. Diagonalize. That's a good guess, because now, because yes, you are right. This A is a symmetric matrix. You can know, and there is a theorem in the theory of matrices that any symmetric matrix can be orthogonally diagonalizable. So we have to find the orthogonal matrix with which we can diagonalize this A. Great. So to evaluate this, we make an orthogonal transformation. So you take an A and you write this A as some O transpose DO, where O transpose O is an orthogonal matrix and D is a diagonal matrix. So you diagonalize this A in terms of an orthogonal transformation. So you will write this integral G3 in terms of this OD, O and D's. That means you just write the orthogonal transformation version of A inside the integral. Now you make a transformation. Now you take another array or a vector P, which is an orthogonally transformed version of Q. It's like an rotating the vectors in orthogonal space, because rotation matrix is like orthogonal transformation. So you take your Q's, a vector, and you rotate it. That's your P. It's something like that. Now your integral measure, which earlier was d and q, is same as d and p. Why it is same? Why this integral measure will be same? Because I have rotated. I have changed q to p by some transformation. Why it has to be same? Or it will be, or it won't be. There is a question mark. Will it be same? How measure change when you do a transformation? This is an integral measure, so it must change. How it change? If you do a coordinate transformation or something like that, probably you have some tensor classes or vector space classes. Yeah, correct. You need to change by some Jacobian factor. Exactly. So if you do a transformation, the integral measure change by the Jacobian. But here I didn't written the Jacobian factor. Why? So I must write some j times integral of dn of p. Correct? Is this wrong? I haven't written that Jacobian. So am I correct or not? Yeah, you're correct. Yeah, we need to write some Jacobian factor. Probably I missed it. So should I change this? I mean, you can unmute yourself and you can speak. That's the whole point. So the point is that this transformation is an orthogonal transformation. So the Jacobian is 1, nothing else. Because for orthogonal matrices, if you calculate the Jacobian, you will find that that will be exactly 1. The Jacobian determinant will be exactly 1. That's why the integral measure won't change. So you can directly write dn of q to dn of p. So if you write that, you can write your integral in terms of p and d and p dp. Okay, so g3n is now is written in terms of our new variable, new array p, and exponential is written in terms of the diagonal matrix D. So as D is diagonal, you can write this P transpose dP as this some pi square dii, which is the entries, diagonal entries of diagonal matrices, and you can sum it up. So you can write this as a summation over dii pi square, and that will give you the answer, which is this. Can you see why? Can you see the answer if you just write this in terms of a summation? Is this clear to everybody? Can you see the answer actually? How you get it? I've written this P transpose dP as some diagonal entries dii and pi square, and by doing that I just get the answer, which is this. Can you see it? So what you have here, you have an multi-dimensional integral d dp1 dp2 dot dpn. Now inside that exponent you have this summation dii pi square. So you have entries like d11 p1 square plus d22 p2 square plus dot dnn pn square. Now you can break this exponent in n factors. So you can write this exponent in terms of n factors. So you have an exponential of minus half d11 p1 square, similarly exponential of minus half d22 p2 square, and so on. So each and every exponential term you can break it, you can break the summation, and you can write as a multiplication. So you have a product of exponentials. So you have a different product in terms of dp1, dp2, and dpn. You have a product of exponentials, and each and every exponential term is a Gaussian integral. So you have a product and you have a Gaussian integral inside that. So now what you can do, you can do each Gaussian integral in that product, which is the same, and that will give you 2 pi by d11 to the half. So then you have another 2 pi by d22 to the half. So you have all these diagonal entries of the matrices. So if I just write it down, let me just here, let me just give you glimpses. So what you can do in this integral, you have a factor like exponential of minus half d11 p1 square integral over some dp1. Now this integral you can just evaluate. This is just your usual Gaussian integral. So you will get 2 pi by d11 to the half. So this will be your answer. So you have similar integral, but you have n such integrals. So you have 2 pi to the half d11 d22, and you have all the diagonal entries. So you will get at the end you will get a product d11 d22 dot dnn, and this product is nothing but your determinant of d, because you have a diagonal matrix and all product of all the diagonal entries are your determinant of d. And as you get this determinant, as you get this diagonal matrix via an orthogonal transformation or a similarity transformation, this determinant of d is same as the determinant of a. So I have changed this determinant of d by determinant of a. I think now it is okay. So you have determinant of d, and you can replace the determinant of d by determinant of a. So now I think it is okay to see this integral. So that's why I got this answer. So far so good. Any question? Okay, fine. finally, but not yet complete, we can still generalize this integral. Your earlier version, that's q transpose a q plus b transpose q. Now you have a more ugly looking integral. I have generalized it. Now how to do this? I described how to do the earlier version of this integral, which is in terms of determinant of a, and now I generalized it. Now how to do this integral? Because you know the title of the talk, they are ugly integrals. I'll come to the pretty diagrams later on in the talk. First, let's do the ugly integrals. Anybody? Any guess how to do this integral now? It will be a warm up kind of things, integral after integral, and we'll make it complicated and more complicated and more complicated. That's how we go. Any guess? So earlier, I think somebody is telling that you can take a maxima of this. You can do the same because earlier you see your simpler version of this integral is this. This is the familiar version of this integral to you, and how you solve it. You take the exponent and you take a maximum and you subtract it from your exponent and you complete the squares. Similar thing we can do, I think, here. How to do this? From the same analogy, you take this exponent, which is this. Now they are written in terms of matrices, and I can write them in components like this. So we'll do a similar procedure. So you take p of q, which is now written in terms of matrices, and you now write that like in terms of the components. Now I'll take the maxima. So I'll take a derivative with respect to qk of this quantity. Now this is qi and this is qk, so this will give me a Kronecker delta. Similarly, this is qj and qk will give me a Kronecker delta, and here is also a q delta jk. So at the end, if you do that, you will get minus akj xj plus bk. So now you can solve for this xj. What is this xj? That will be A inverse B, nothing else. Because these aij are matrices, so you will get xj by taking an inverse matrix, multiplying by the inverse matrix. So x is A inverse of B, and your P minima is 1/2 B transpose AB. Exactly same. If you see your earlier version, you see 1/2 B 1 by AB. This A 1 by A is nothing but your A inverse. So you can do it by analogy, nothing else. So now you subtract from PQ, your P minima. You subtract and you take it common, and you'll get a new kind of array, which is Q minus A inverse B transpose A Q minus A inverse of B. Now we do the same trick. I redefine this Q minus A inverse of B, and that will give me the answer. Because if you redefine this, this will be the earlier problem. Exactly. This will be like this. Q inverse. This is P transpose AQ. And we know the answer. That is this. So these factors comes from that. And then we have this factor. This factor is exactly your P minima and exponentiating P minima. And this factor comes from the earlier integral. So we solved it just by analogy. So is it fine to everybody? Any doubt about how you solved it? We just take the lesson from our earlier integral and we exactly solved it by redefining some variables. So you have a factor of exponential of half B transpose A inverse B and another Gaussian integral in terms of your matrices, but now Q's are replaced by some P's. That's it. Now you can do the same trick. as you did in your earlier integral, and you can solve it, and we'll get this factor 2 pi to the n by the determinant of a whole to the half. Fine. Okay. So far, so good. Now, the last kind of generalization we have, and that will give you a glimpses of your quantum field theory. We are almost ready for the beast. Now, I'll give an integral which is defined by z, that is for a notational convenience in quantum field theory, and that integral has a function instead of this q array. Now we generalize this as in terms of, you can think them as infinite dimensional arrays. So you have a measure which is d of some function, and in your integrand you have exponential of minus half. Now you have fx fy, so I have to integrate over dx dy, because you can't now take a transpose and just multiply like a matrix. These are functions, and now you have some kind of an matrix kind of thing in the function space which is like in some operators. So that's why I put a cap. And here you also have a general version of b, which is b of x, and integrated over a of x. So this is the kind of integral we need to do. But this is not a familiar integral, but this is the next step. And this is the kind of integral you need to do when you do quantum field theory, or you do path integral quantum field theory. But this is nothing else but a generalization of your earlier integral, that is in terms of matrices. So that's why I want to motivate that you can do this integral exactly the similar way you do the earlier integral. You just think mentally that these functions f of x are not just functions, they are like an infinite dimensional arrays in the function space. So you can do an integral, you can write them like an array, you take the answer from your earlier version, and you elevate all those operators in terms of functions or operators or arrays. So it is very similar to this integral. So you think of this a xy as some matrix A, and you think this f of x as some n dimensional vector q. So you know the answer for these two versions, that is q and a, that is this. So you go to the function space, you take the answer and go to the function space and you write it exactly, just by analogy. I haven't done anything. You don't need to solve it. You need to find this determinant of a. We will talk about how to find that determinant, and you will have this. You just have to integrate over. You can't now take a transpose of b, but you have to integrate over dx dy as these are functions. So you need to calculate this a inverse. I don't know how to calculate inverse of an operator still now. I don't know how to calculate this determinant, but this is what you have to do. Now, any idea how to calculate these two? So, any idea how to do this? How to take an inverse of an operator? How to take? Okay, let's tell me how to calculate this determinant of a of xy. Any guess? Any guess? How to calculate this determinant? You are in a function space, so any idea how to calculate a determinant of a xy? Xy is some kind of an analogous to some operators in your function space. Can you guess? Using spatial, what kind of spatial functions? You don't know. I don't know what kind of spatial functions you have, but this is some kind of an operator in your function space. This is like an inverse of some operator in function space. So what are they? I mean, how to do that? How to calculate it? People are living, getting frightened by the answers, maybe. So this I can say, this is very easy. Aha, yep.
Good guess. Inverse is like Green's function. Exactly. An operator inverse is like Green's function. I mean, if they satisfy the Green's function conditions, of course they are Green's function. But for that we need to satisfy some conditions to make it a Green's function. But what about the determinant? That is much easy to answer. I mean, you can, if these are operators on some space, some function space, what you can do, you can uh, take some eigenfunctions of those operators and you can write an eigenvalue equation. So taking a good basis, you can write the eigenvalue equation of those operators and you just take a product of those eigenvalues and that will give you the determinant. That's one way to solve how to get the determinant. So in function space, you can write an eigenvalue equation for a of xy. So a of xy acting on some kth f function is lambda times f, and you have an eigenvalue equations, and you take all such eigenvalues and you take a product of those. Now there will be some point mathematicians will come and say that, oh, hey, you can't take those kind of infinite products, they don't converge and all such. I don't care about those bullshits. I mean, we assume these functions are very smooth functions, and we are physicists, so we always assume the functions are smooth, and those products are converge always, and they will give us good determinant. So we have the determinant. We don't care about the mathematical juggleries involved in here. So we think we can write the eigenvalue equations, we can take the product, and we have the determinant. That's it. And what about the inverse? Now, as this was said, that inverse can be found as a Green's function if they satisfy some condition like this, that if you take an integral over these functions, if that give you some delta functions criteria. I just denoted this A inverse by some d of f kind of things, just for notational convenience, and that will give you the, you can, if you can solve this integral for d, you will get what is inverse of A. So far so good. Happy? Now I don't think it is that much furious as it looked earlier. So any questions at this stage? Because it will going to be uh, I will switch gears from now on. Any questions? Anything you didn't understood? Anything is not familiar? You can just yeah.
How
Hello.
can you assume? How can we assume that infinite number of eigenvalues will give rise to a finite number?
That is what I told. That is what I told. That is what mathematicians comes and will tell me. But I assume that this infinite product is convergent product, and we have sufficient. We have all the eigenvalues, so they are sufficiently convergent. So you have to take the limit, and you have to take why they converge and the convergence criteria. You have to take those convergence of products, infinite product. But you can calculate, if you see, you can calculate this determinant by taking just the product of eigenvalues. They are infinite number, but you can go to some subspace and you can calculate the product in that subspace, and you can take infinite product in each subspace like that. I mean, you can assume that function space is divided by some subspace, so you can diagonalize in that subspace and you can calculate the product in the subspace. Is not can't be not has to be an infinite dimensional subspace. So there are ways you can calculate, and in physics, the problems you will encounter there, this determinant has a good properties, and you can easily calculate. There are other ways which I don't want to go into that to calculate this determinant. But if I want to do a path integral course, you will see how to calculate this kind of determinants. These are not as hard as you are thinking. So they are just
But but the
mathematically,
but
yeah.
the moment we will choose a subspace, aren't we restricting on the values of x and y?
Mm-hmm.
I mean, the
Um,
integral is no more. I mean, we can't run the integral from minus infinity to plus infinity.
That is fine, because the other part will be zero, let's say. So anyway, you can do that integral. I am not talking about the integral still now, because integral I can do. If I know the df, I can do that integral. I will come how to do this integral. I don't talking about the how to do this integral, but still now I am just concerned about how to do. And anyway, this is a constant factor, So you can put under a carpet, you can just call it z of some constant, and you can put under the carpet of some constant. So what is important is this integral, not this front factor, because they are just constant. That's the determinant. So you can just put it under a carpet, there is a constant, and z is proportional to this integral. That's it. You don't need to care about much about this constant factor. All the physics are behind this integral. If you are not mathematician, then you don't need to care much about some constant factors. Anyway, okay. So now we'll go a step further. So we'll take a step back and we'll introduce something interesting, an interesting observation. So earlier you have this integral. In step 2 we have done this integral with this parameter a. Now if you differentiate this integral with respect to a, what you will get? So I can take a derivative with respect to this parameter a, and that will introduce a factor of q square in front. Can you see? So if I take a derivative with this integral with respect to this parameter a, it will come as a q square, factor q square. Now for a notational convenience, I will define an average of q square by this. So this is like your Gaussian probability distribution function, and you do it some in statistical mechanics. It seems like some moments, calculation of moments. This is familiar? Does this familiar to you? So this is like a Gaussian probability distribution of q square. So this q square is like some kind of a moment. So you can calculate this q square as an average of q square. So what is this q square? You have this answer. You have this answer right hand side. You can take a derivative with respect to minus 2 dda of this answer. So you can write down what is this q square. Can you do it? I leave it for you to write down what is this q square. You have to just take the derivative on the right hand side. Rather, I'll give you a more difficult one, which is this, which is a repeating version of this. So you repeat this n times, so you will get average of q to the 2n, which is given by this. Now what will be the result of this? Can you guess? Can you guess the result? So everything I am motivating you, you see, you do something and you will just motivate some kind of integral without doing it. Actually. So you have to take a repeating derivatives of your earlier answer, which is 2 pi by a whole to the half. You just repeat it. You just take derivatives n times with dda. So can you guess the answer? Any guess? Then I'll tell you. No one? You have to just take the derivative. It's easy. It's 2n minus 1, 2n minus 3, dot, 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 5, 3, 1. And with a factor of 1 by a to the n, which you could have guessed from a dimensional analysis. Because this exponent, this a has to be of dimension of 1 by a square, and from the dimensional analysis you could have guessed this a to the n. And this is the product. If you each time you take a derivative, you will get a 2n minus 1, 2n minus 3, 2 5, 3, 1 from n times. If you do it n times. Is it okay? Can you see the answer? By taking repetitive derivatives. Now what is this? What is this quantity? This 2n minus 1, 2n minus 3. Mathematical physics. Let's check how much mathematical physics you have studied in your bachelor's. Do you know what it is? Yep, it is a double factorial. Yes, exactly. It's a double factorial. So your q2n average is 2n minus 1 double factorial over a to the n. Now how you remember this double factorial? How you remember this answer? To remember this answer, let me give a trick. You imagine you have 2n connected points. I will give a simpler example. You imagine you have 2n connected points and you just pair up. So first point can be connected to 2n minus 1 point. The second point now has a 2n minus 3 chances to connect it to the other points, and so on. So for example, if you have q to the 6, you have q, 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 q. You just write it like this, and you just connect each and 2 points. So the first point can be connected with all these 5 points. So it has a chance to connect to the 5 points. Then if you connect 2 points, q and this q, then the second q has to be can connect with all the other 4 points, or all the other 3 points. This is connected, so there are three possibilities to connect. So you have a factor of 3, and then the other q only have one chance to connect. So it is 5 into 3 into 1, so it is like 15. So this is like 5 double factorial. So this is how you can remember. You can just write the q separately, and you can just connect pairwise. So this is called Wick contraction. This is by G.C. Wick, and this is known as Wick's theorem. So this is what we'll use many times in quantum field theory when you do perturbative quantum field theory. Now let's generalize this for vectors. For step 4, we have vectors. So now you have this. I just replace this b by some j, which is looks like a source. So now, and I put an I factor, because we are physicists, and physicists like to introduce anytime I factors when they want, and that's why I just introduce a factor of I in front. I just replace this b by j with some analogy with quantum field theory, where this j is treated as some sources. And you know the answer. I have written the answer in the just putting the I factors. So now, if I do the same thing with this quantity, what should I do? Now I can take a derivative of this with respect to p times with respect to this ji, jj, jk, jl, all the j's, and then put j equals to 0. So if I take a derivative with respect to j once and put j equals to 0, we have a factor like this. Okay, with a xj. Then if I take ji, jj, I have a factor xij. So what will be this xij average? If you calculate this, that will be aij inverse, just analogous to this q square. Probably you have done the calculation by now, and you got the answer as 1 by a, which is nothing but aij inverse. Now if you take odd elements, they will just vanish. Can you see? If you have odd number of elements like xi, xj, xk, they just vanish. Why they will vanish? So always you need some even number of terms, q square. The odd elements, if you take xi, xj, xk, all odd averages will vanish. Odd products of average of odd products of xi, xj's, they will vanish, because you see this probability distribution, as we are thinking them now as a probability distribution, they are Gaussian, and it has moments, which is the second moment, because the mean is 0. For 0 mean Gaussian, you have a second moment only, and for the second moment, if you calculate average of odd elements, they will exactly vanish, because you can change x by minus x and they will give a minus. So this exponent won't change, but the integral change by a minus sign, and that will exactly vanish. For all odd elements, it will vanish. So the next element, next non-zero element, will be some four point correlator, as they called, or some even correlator. So these are like correlation functions, as you calculate in statistical mechanics. So you have all the even correlators. They are given by this product of inverse matrices with a Wick summation. So for example, if you have 4 such numbers xi, xj, xk, you just connect, because this distribution is like a Gaussian distribution. So you can write all the other moments in terms of your second moment, that is xi, xj, as a product of your second moment. So you just do the trick. So you can connect xi with xk and xj with xl. So you have a product xi, xj, xk, xl. Then you can connect the other two, and you can connect the other. So all possible contractions you will take from this, and that will give you this correlator, this 4-point correlator, xi, xj, xk, xl. Is this okay? Anything need difficult here? So this is just a contraction. You can just connect each and every pair and just write as a product. So first term you can connect to the second, and you have a 6-point correlator. So all odd correlators you can write in terms of this 2-point correlator. That's it. So this is what is done in quantum field theory as a weak contraction. This is known as weak contraction. We do it in fields. Now here we are doing in terms of x's. Same thing we just do in terms of x's. We have phi 1, phi 2, phi 3, phi 4. You have 4 fields, and you take a correlation function of those fields. You just connect them. That's it. You can write them as 2-point correlator. So at the end, what you need to calculate is a 2-point correlator in quantum field theory, and you can write all the other correlators in terms of those 2-point correlators. That's it. That is your weak theorem says. Is it okay? Now we are mostly at the end of the talk. Is there any question about Wick's theorem and so? No question? Okay, fine. So we are all set. Let's do field theory. So we'll directly introduce you to the path integral quantum field theory in 5-4 cases, 5-4 interactions. We jump into the, don't be frightened by the name, because everything that will come after this heading, that will be familiar to you because you are all done with the mathematics. Now we can do quantum field theory directly. You can jump into the calculation. You can do a calculation in quantum field theory like a quantum field theories. Can you discuss? Okay. So what you do, you can take these 4-point correlators and you can take all the pairs. So xi you can pair with all these 3. So you first take xi with xk, then this xj remains with xl. So you can write as a product of xi, xj, xk, xl. So what we are doing, we are just calculating this quantity. If you calculate this quantity for 4-point functions, you have xi, xj, xk, xl. And if you calculate that, you have a product of these aij's. So for ai, aj, ak, al. Then you have another product where you can just switch the permute the indices. So you have other products like dil, djk, then dik, djl, like that. So what you are doing is nothing but you are taking this connections. So you are taking this xj, you are connecting with xk. So you connect first these two, then you take this and you connect with these two. So you get the first two, this term, ik, this term. But this is not the unique one. You can also connect this with this and this with that. So you can take another connection. So you can take first this with this and then this with that, and that will give you this term, first term. So you can write this as a sum of products of 2-point correlator, like this, by some contraction. But every one has to be contracted, because if one is left out, that integral will be 0. So everything has to be contracted, because that will be odd man's out, and if there is an odd man's out, that will be 0. That will give you 0 contribution. So the contributions only comes from all the paired ones. So all 2-point correlators, else is 0. That's it. So now it is clear. Okay, fine. So let's do field theory. Now we'll jump into interacting 5-4 field theory in path integral methods. So goal is to evaluate this integral. So this is exactly the integral that comes in 5-4 theory. This is what is 5-4 theory, and this is what is 5-4 action. So you will write your scalar field action in the integral, and this is what is known as a path integral directly. So you can write down this path integral in terms of d phi. This phi you can think as a function of x. This phi is a function of x, where x is a space-time point, not a spatial point, but a space-time point, and this is your scalar field action. But if you assume that these fields are sufficiently rapidly decay such that you can neglect the boundary terms, you can just do an integral by parts here, and you can write this as this, like this. Now this is very familiar thing, because this is nothing but your uh, box square operator, box square plus m square operator. This is your Klein-Gordon field, Klein-Gordon operator, and Klein-Gordon operator acting on Klein-Gordon field, and that will satisfy, this phi will satisfy the Klein-Gordon equation with some sources j. So this is a with source Klein-Gordon equation. You can see inside this, but this integral from a mathematical point of view is very familiar. I mean, if you don't understand what they mean, but still you can solve this integral from the point of view as an integral, because this phi is exactly analogous to your f, and this del square plus m square is analogous to a. But this a is now a differential operator rather than just a function or a matrices. So how to find out the inverse of this operator? So you remember, you have to find out this inverse. So this differential operator acting on some Green's function give you some Dirac delta function, and you can find out the Green's function for your Klein-Gordon operator, and you will find out this d of x minus y. But believe me, this is very simple. You don't need to do that, because there was a guy called Fourier who gives some tricks that you can convert all the differential operators to some algebraic operators, and you can take an inverse directly. So don't worry about these Green's functions, but you can see that this integral is nothing but some constant, as I said to Niladri, that we can put this under the carpet, this some constant with e to the power omega j. This omega j is same like this. This is exactly the thing we have done. Let me show you this one. We are exactly doing this. So this is the c factor, and this factor is your omega j. So okay, so this omega j you can just readily read out from this integral, because this integral is exactly familiar. Any question about this point? I hope the integral is clear now. Now we are doing quantum field theory. Readily we are doing quantum field theory, and this is the free field theory. Believe it or not, this is the exact solution of your free field action, and this is j is called the partition function in your free field theory. And you are solved with the action if you can solve this for sources. Jx are like sources. So this integral, you can think now, you can physically interpret this integral. Now this jx is like a source, and this dxy is like a propagator. So you can now think them from a quantum field theory point of view. You can now think them as you have some kind of source which is like these j's. So these j's are like some kind of a source. So you have some jx or j of x, and you are propagating from j of x to some other sources. So you have a creation of particles, and that particle propagate by some propagator d of x minus y, and they got destroyed at some j of y. So you have a source and a sink, and you have a propagation in between. So you can physically interpret this process. This is an absolutely physical process, and these j's are the source of the particles. They create particles or annihilate particles. So you have a source, then you have a propagation of the particles by d of x minus y, which is a propagator. This is called the Feynman propagator, and you have a sink, which is j of y, where this particle goes. This is how we interpret this integral in quantum field theory. Okay. Now, how to calculate this propagator? Now I told you that we can write them in terms of Fourier modes. So this Dirac delta function you can write in terms of a Fourier integral over k space or momentum space, and you can just, now this del square operator acting on e to the power I kx is k square. It is an algebraic operator. So you can just take an inverse and do a Fourier integral. Now this I epsilon prescription is given by Feynman just to avoid some mathematical complications comes from the singularities in the complex integral in the complex plane on the real axis or something. But this integral, don't worry about this integral, we don't need this. too much, but this is integral is called the Feynman propagator for free field theory. Okay, now we are ready, we are done with free field theory, nothing more. So we can go directly to interacting field theory. So I'll give a kindergarten version of the problem. I don't do interacting field theory that much. So let's do interacting field theory. So any question about the free fields? We are done with free fields. Any question at this point? Anybody? All set? Are you ready for interacting field theories? Okay. Let's give you the beast. So this is a baby problem or a kindergarten version of interacting field theories. So this is my 1/2 m square q square is like this phi square m square. This is like m square phi square m square phi square term. Then there is a source term which is j of q, and now we have added a q to the 4 interaction. This q to the 4 makes it formidable. Now for lambda is equal to 0, you know how to solve this problem. But if I put this lambda q to the 4, can you solve this problem now? Anybody? Can anybody dare to say he can solve this problem? Can you solve it? This is a non-linear function in q to the 4, but it's a fourth order function, not in third order or second order. Second order you can solve because you can do Gaussian integral. Gaussian integral we know how to solve, so we can solve q square. But now I have added a q to the 4th term. So this is like an interaction term in the action. So this, the quantum field theoretic analog is exactly this, but this will be phi to the 4, which is called phi 4 interaction. But let's do a baby version of that problem. So can you solve this integral? Anybody? Whoever left here. Any idea how to solve this problem? Can you give any insight how to solve this? Nobody? You know the answer for lambda equals 0, but you don't know the answer for lambda non-zero. So what you can think of?
Feynman space.
What you can do, you can just expand. So first of all, I just want to make a point that there is a trivial point that we can scale this q by m, which is z, which is given by this. So all the mass parameters, all the parameters are scaled, but we don't do that. Okay, for lambda equals 0, this is just your familiar Gaussian integral. You know how to solve this. For lambda non-zero, what should we do? You expand this zj in series of lambda. So you can expand this in series of lambda. So you can exactly expand all the lambdas because it's exponential in lambda. So you can expand in series of lambda. And you can integrate term by term. Now how to do that? How to expand and integrate term by term? Looks familiar? Any guess how you can integrate term by term? This is a very ugly integral. Now pretty diagrams will come to save you.
It's like just calculating the moments.
It's like calculating moments, but how you can do it quickly? Each and every time you have to do the integral. You see, just observe that a general term will be like this. So this Gaussian probability distribution kind of thing tends q to the 4n. But this you can write it as some ddj of 4n of this integral. Okay, so you can write it as this, like ddj of 4n of this integral. So what you can do, you can write this zj as a series of taking derivatives. So this is an derivatives with respect to operators of all order, ddj to the 4, ddj to the 8, and all other orders of derivatives up to 4. A general term we will like ddj to the 4n, which is very 4n. Now what is this? What is this series in front? This is just an exponential series in ddj's. So you can write, you know the Taylor expansion. Your Taylor expansion you can write as e to the power a ddx, something like that. So this is similar. So this series is nothing but exponential of lambda by 4 factorial del j to the 4th. Now that will act on this integral. So this is an operator, exponentiation of some operator del j to the 4th, the 4th order operator. But this integral you can readily do. This integral is 2 pi by m square whole to the half 1 by 2m square j square. So now you have the solution, but you have an operator left out. So you have two exponentials, one in lambda, one in j squared. Let's actually. So now now you cannot exactly solve this integral. You have to take all the orders of derivative. There are all the orders of lambdas and all the orders of j's. But order by order, you can pick any orders of calculation you want, and you can do that. So this is like a perturbation series in your quantum mechanics, where your parameters are lambda, and you can just write down your zj in terms of double exponentials, one in lambda, one in j's, and you can now pick any orders you want. Just like if you want the order lambda calculation for j square or j to the 4, you can get that. Okay, is this okay? Everything is good? Okay, let's progress. So by expanding these two exponential obtained, you can like a double series. So for notational convenience, let me define this z00, which is this 2 pi by m square. So now, for example, if we want lambda z to the 4 in z tilde, which is this, if you want this term, you want a lambda z to the 4th term. So what you do? So you take one z to the 4th term. So what you do? You will take, see, there is 4 derivatives of j, 4 derivatives with respect to j. So you have to take a z to the 8th term from this. So after doing 4 derivatives, it will give us j to the 4th term, and you take a first order in lambda here. So you just replace both exponential order by order. So you just extract j to the 8th order term in j square by 2m square, which is 1 by 4 factorial 1 by 2m square whole to the 4 j to the 8, and just replace this derivative operator, exponentiation of derivative operator, by the first order in lambda, which is minus lambda by 4 del j, and you just differentiate. What you will get? You will get 8 factorial by 4 factorial, something like that. You just do it by hand in your home, and you will get this answer. So order by order you can solve. You can extract each and every term order by order. Is this fine? Are you listening or not? I don't know. Everybody slept. So now let's say I want some higher order terms like lambda square. So you can calculate a term like lambda square with j to the 4, which will give you j to the 4 like this. But let me ask, which term you will collect? Which order term you will collect from this e to the j square by 2m square? to calculate this lambda square j to the fourth term? Anybody? Which term you will need from this factor and this factor? So there are two exponentials. You have to pick terms as you want. So there are infinite terms, and you want a term which has lambda square order and a j to the 4. So at which order you will calculate? You just extract from this j square by 2m square. See, here you have lambda square order, so you have to take the lambda square. So you have a derivative with respect to del j, j to the 8, del j to the power 8th order derivative, and you want 4th order in j. So you have a 8th order derivative and you want 4th order in j. So which order of lambda you need to pick out?
Can you explain again how to take order? I mean, I did not
So
understand.
you have an exponential in j. So let me do it carefully. I think I should explain this. So what you have two exponentials. One exponential like this, which is like this, and one exponential is this. So you have double exponential. So each and every exponential you can expand in a Taylor series, and you can have orders like j square, j to the 4, j to the 8, like blah blah blah. Here you have the orders del j to the 4, del j to the 8, then 12, and so on. So now you want to pick up a lambda square and j to the 4th term. So how to do it? You just see, I can replace this exponential by a lambda square term, which is lambda by 4 whole square. Okay, so that will give me del j to the 8th term. So from this exponential, I have chosen the lambda square term, which satisfies this criteria. Now I want the j to the 4th term at the end. So I have to choose a order j to the something, which after taking this derivative will give me a j to the 4th term. So I ask the question, what will be the which order term you will pick up from this j square by m square? Is that clear? So from this term we have taken the second order term, which give you a del j whole to the 8, and at the end of calculation you want the j to the 4th term, because you want some lambda square and j to the 4th. That is the term by term you can evaluate, because you have two exponentials, you cannot just merge them together because they are operators. So which order term you will take for j from this exponential, such that at the end you will get 4. It's just arithmetic. Tell me. So you have a 8th order term.
It's just 12.
So you have to take a 12th order term, no? So if you have take a 12th order from this, then after taking 8 derivative, you will get a 12 factorial by 4 factorials cube and all this such stuff, and you have a j to the 4. So from this you have to take a 12th order term. That means 2 to the 6. So it is j square. So you have to take 1 by 6 factorial. So j to the 6th. You understand? So this is the 4 factorial. You have to take 1 by 6 factorial, 1 2m whole square whole to the 6, j to the 12th. So that's the answer. So here you have to take 1 by 6 factorial, 1 by 2m square whole to the 6, j to the 12. Now if you add this on this, you will get this. That's the term by term calculation I am showing. Is it okay? Fine. Some more. Now you have a lambda square j to the sixth. So you have to take the 8th order lambda square order, and you have to take j to the 14th to get a 6, and you will get something like this. So now you can see some patterns in this, and now you can associate few diagrams, pretty looking diagrams for each and every order. Can you think of some diagrams which you can associate with each and every order? There are not a single diagram for each and every order. There are multiple diagrams that you can associate. So let me show you how you can associate each and every term with some pretty looking diagrams. So what you have a lambda order term and you have a j to the fourth term. So this lambda is connected to some 4 factors of q, as you remember. So for each q you write this lambda. So for each q I have written small legs, and you have a 4 j's which is like some sources. So let me mark it: j1, j2, j3, j4. So what you can do, you can connect the all possible ways you can connect them. So what you can do, you can connect all the legs to this lambda. Okay, so neater way is to write like this. So this is lambda, there are 4 j's. So this is a lambda j to the 4th term. But this is not the only term. You can connect this j1 and j2 itself. So let me call it 1, 2. This is point 1, this is point 2, 3, 4. But you can connect these two, and you can connect these two. So what about this lambda which has a 4 legs? You can connect them as well. So this is like your term by term expansion. So each term you can associate with all these little looking diagrams. This is like connecting your x's. You know the weak contractions that you can connect one x and one. So you can make this, associate these diagrams with all these terms, and you can calculate which factors, and that will give you the all the other factors you have. So for each term you can just associate these diagrams. So let me draw few more for you. Okay, sorry, up. Sorry, yeah. So I can draw a few more, where 1, 2, so you have 4 j's, 3, 4. Now 1, 2 I can connect like this, 3, 4 I can connect like this, but I don't do that because I have this lambda. So you can connect this with 3, this with 4. Other 2 points remains, you just connect them both. So, but this we usually not draw like this, but we used to draw like this, 3, 4. These are all lambda j to the 4th order term. Okay, so these are your pretty looking diagrams. So you can got 3 terms. So we got 3 terms: this, and this. Now you see, among them there are few terms where these are like all connected with some vertex. This lambda is called a vertex, where you have a 4 points associated with it. It's called a vertex. Now these are like disconnected diagrams. So you have lines and you have some loops, some kind of a loops which is outside. Now how physically interpret them? Now these has a very good physical interpretation. We don't go into that, but let me just explain hand-wavingly. So you associate the propagation of particles from like that. So you can have a diagram, you can also connect diagram like this. So you can have 1, 2, 3, 4, and then you can have like this, some bubble. Now this is like gives you a propagation of a particle from 1 to 2, and then it is give you a propagation from 3 to 4. But this is like a single propagator, and these are called a vacuum bubble. In Feynman diagram language, these loops like these disconnected loops are called vacuum bubbles. This is like you have a quantum fluctuations happens in somewhere else in the universe when you have a propagation from 1 to 2 and 3 to 4 of some particles for for 4 different sources and things. So these vacuum bubbles are like quantum fluctuations happen from elsewhere. So when you do quantum field theory, you will get these vacuum bubbles inside, but they don't actually contribute in the process of scattering or the process you want to study. The important processes are like this, where you have two sources, where you have a propagation of particles from one point to another. So the actual important processes are not those vacuum bubble processes, but this kind of a process where you can have a propagation. So from J1, let's say this is J2, this is J3, this is J4. So two particle propagates, they have done something and they go out like this. So these kind of a processes are like analogous to the scattering theory you have done. So in between you have some region, scattering region. So some particles comes with some momenta p1, then another particles comes some momenta p2. They go with some other momentas p3 and p4. So these are analogous to some scattering processes that you can have. So these are some physical processes. These vacuum bubbles are not contribute to any physical processes. So in quantum field theory, we actually ignore the contributions of this vacuum bubble. But this process is something else. This has connected with some internal, so this is an internal loop connected with some propagation of particles. So it's like a particle propagated. So let me call it 4 and 3 and 4, just to 3 and 4. So from 3 the particle goes from this point, which is some lambda, and they go on a loop, take a fluctuation, and then they goes on to 4. So these are like loop corrections, and these loops actually contribute. So you can take these loops, you can cut these Feynman diagrams. So 3 to some intermediate points you can do, and then you have a 4. So these are like correcting factors, and they actually contribute in physically what is called a mass renormalization when you actually calculate the Feynman diagrams. So what are the other diagrams for the other processes I have written? So I have shown you uh, different orders. So for different orders like lambda square, j square, you can associate similar diagrams, which is like this. There are many more diagrams. This is lambda square, j square. So this is all the vertex are associated with lambda. All the endpoints, external points are like your j's. The external points are sources. All the vertex where there are 4 points meet together, they are called the vertex. They are the lambdas. So this is lambda squared due to the fourth term. And you can associate all sorts of diagrams with it. So all are second order in lambda and fourth order in j. So can you see the connection?
Can you explain the mass renormalization thing?
That I cannot explain now. For that you have to do quantum field theory really. We are
Okay.
not doing quantum field theory here. I mean, how then we have to calculate the diagram. We have to calculate that integral. This each and every diagrams are associated with some integrals. We have to do a baby problem, baby version of that, such that I can just introduce to you some other day. I can discuss how to calculate the integrals using from these diagrams. That will take some 2 more lectures on this. But this
Yes,
is just
yes.
to give you a glimpse of how you can associate with each and every each and every term, order by order, or the perturbation series. Each and every term you can associate a diagram. These are exactly the Feynman diagrams you have in your quantum field theory, and you can. These are physical processes or 5-4 processes, but you can calculate the contributions for each and every diagram, and that will give you the scattering amplitude. So this is the lambda square j to the fourth order term. You have a lambda square j to the sixth term which looks like this, and etc. So you can play with it, you can draw, you can calculate many more terms like lambda to the fourth term and j to the 12th term, and you can draw the Feynman diagrams you want. So there are some rules to draw these diagrams, that for each and every vertex there are 4 points. So if these 4 points are connected with the vertex, so you have lambda square, that means you need at least two vertex. So this is the two vertex 1 and 2, and all there are external points is this external points is associated, and for each line you have to associate this 1 by n square factor. So for each vertex you will associate a minus lambda factor, so that's why it is a lambda square order correction. So each vertex you have a minus lambda factor, each line you have 1 by m square factor, so that will give you 1 by m square to the sixth, which you get here 1 by n square to the sixth. That comes from this lambda square correction. 1, 2, 3, 4, 5, 6. So there are 6 lines, so you have associate 1 by m square factor to each line. And you have all the sources, you have to associate the sources with all the external points. So these are the j's. So you have a factor j to the 6th, 1 by m square to the 6th, and minus lambda whole square, which is this factor. Don't worry about these front constant factors, they don't actually you need this, but you can just have this 1 by lambda square, 1 by n square to the 6th, and 1 by j to the 4th. So you have the rules to get to the answers coming from this, and each and every diagram will give you the same factor. These are the j's, these are the 6 j's. So you have 7 lines, 1, 2, 3, 4, 5, 6, 7. So you have a 2 to the 7 factor, 1 by m to the 7, j to the 6, minus lambda whole square. Okay. Now, as you see, there is another point I just want to mention and want to conclude, that there is an obvious point that you can also expand this zj in the power series of j rather than power series of lambda. So if you expand them in terms of power series of j, you will end up with this, which is like an integral over q to the 4 with a q to the s. Now this in field theory is by analogous of what is called the Green's function or the correlation function. So that's why this j is called the generating function of your correlations or Green's functions. So this is actually the observables you do in quantum field theory. You will calculate these correlators, which or GS, which is the analogous of Green's function in QFT, and like in G to the 4th order, if you want to calculate this, you will get something like this, which is the double factorial, and you will see this numerical factor is exactly like the j to the lambda j to the 4th order. So either you can expand them by in the power series of j, or you can expand it in the power series of lambda, they will give the same answer. I mean, it's immaterial, but so you can compare these two power series and you can write the correlation functions in terms of the derivatives of those operators term by term, and you will get the correlation functions. So your correlation functions or the Green's functions are nothing but sum over all those Feynman diagrams. That's the whole point in perturbative quantum field theory. So that's how you do perturbation series in quantum field theory, in terms of Feynman diagrams, in terms of those pretty diagrams. Now in those diagrams, as you see, these diagrams are all connected with j's. These are like disconnected diagrams. There is no j. These are like they are closed inside. So all the j's are like these vertices, these open end points. These are like j. So if you just see that we can write this zj, so you can write this z of j in terms of some z of j is equal to 0, and then some e to the power I omega of j. Now these j of 0 contains all disconnected pieces because they are independent of j. So what actually is relevant is omega w of j. If you know what is this w of j, then you can extract out the connected pieces which actually contributes to your scattering processes in quantum field theory, and you can calculate the decay rates, you can calculate the cross section, you can calculate the scattering amplitude, its matrix, and all those stuffs. So that's it. That's what I want to tell you. If you want more some other day, so goodbye for now. Any questions? Yes, you can ask. You can just unmute yourself and you can ask.